Okay, so next up is Mukund, who will tell us more about correlation functions in AdS CFT.
Okay, so what are we going to do today? So yesterday, I gave you a prescription to compute correlation functions using the AdS CFT correspondence, and today we'll actually do a computation of some correlation functions. I will give you an explicit computation of the 2-point function and sketch how the 3-point function computation is done. Well, or rather, I will do the computation modulo an integral, which I will leave as a homework exercise. Okay. So what we want to do here is to figure out a way to compute 2-point functions of gauge invariant local operators in n equals 4 super Yang-Mills using the AdS CFT correspondence. So I'm not going to do any computation in the field theory. If you were to do the computation in field theory, in perturbation theory, you would just do the standard Feynman diagram expansions, do the standard big contractions, and obtain the 2-point function. What we rather want to do here is to use the dictionary we gave yesterday to find first the generating function for 2-point functions and take the variational derivative of that with respect to the sources and write down the answer for the 2-point function. And you've seen an element of this computation already yesterday in Larry Yaffe's talk, where he worked out for you the 2-point function in a thermal field theory in a black hole background. I'm just going to do a much simpler version of that computation for a scalar field in AdS background. The advantage being I can do the computation explicitly in real time. So let me set up the bulk computation. I'll take a scalar field which now I will call phi, which propagates in AdS phi. Okay, and I'll choose my metric for AdS phi to be the Euclidean metric in these coordinates, the Poincare coordinates, and the action for the scalar field propagating in this background okay. So this action you should think of again as a reduced action where the mass has been obtained by doing some Kaluza-Klein reduction on the phi sphere. For our purposes, we'll just leave m as a free parameter. Further, I have restricted myself to the action up to quadratic order. I'm not going to worry about higher order interactions in this action because they're not going to be relevant to the computation of the 2-point function. When I later come back and sketch the 3-point function, it will become clear that I will need to go beyond this order to worry about computing a 3-point function. But for the 2-point function, this is good enough. Okay. So what we'll first do, we were instructed to do yesterday, is we'll solve the wave propagation of the scalar field in that background subject to boundary conditions. Okay. And the boundary conditions I'm going to choose is the following. I'm going to ask for the field phi at some value of z being epsilon to be phi naught position given by its value, a function of the boundary coordinates. Okay, so here there was a comment yesterday that I would need to worry about regulating the theory. So I'm regulating the theory by explicitly cutting off the small z region by putting hard wall boundary conditions at z equals epsilon. We'll see why this is important in a moment. Okay, very good. So let me write down the wave equation, and let's solve it subject to these boundary conditions. The wave equation is simple, where box as before for scalar field is just this. Okay. Let's also exploit the fact that we have full translational invariance in the 4-dimensional boundary coordinates labeled by x, and mode expand the field phi in terms of some Fourier modes as follows. And let me choose a slightly different normalization where P is just the norm of the vector P. So the claim is that the wave equation reduces to the following ODE for the scalar field and I'll explain the notation in a moment. Okay, where U is P times Z. And let me put back my length scale here. I had set AdS radius to 1. Let me put back the AdS radius because I'll keep track of that in what follows. Okay, so this is reasonably straightforward. You just plug.
This is the propagation of the field involved in 5-dimensional spacetime, but you said that this coordinates, this Z coordinate does not cover the whole manifold.
Good.
How do you interpret this?
Yeah. Okay. So I said this for the context of Lorentzian AdS.
Yeah.
For Euclidean AdS, these are good coordinates. These are global coordinates. Yeah. So there's a distinction between the Lorentzian and the Euclidean geometries. So you could use these coordinates to talk about the full Euclidean space, whereas you can't use them to talk about the Lorentzian geometry. So that's an important distinction, and I'll come back to Lorentzian geometry later. Okay. So that's the wave equation. All we need to do is solve this subject to this boundary condition. Now, the claim, which I can prove to you in 2 seconds, is that this equation is something very familiar to you. You should be able to tell me the solutions right away. If you replace phi of u by u squared times chi of u, you find an equation which presumably you all recognize as something you know. It's a reasonably famous equation. Okay. So chi satisfies a Bessel equation, and the solution is a linear combination of the Bessel functions where delta I've defined to be this quantity determined by the mass of the field. Okay, so we have an explicit solution. We only need to do two things. We need to impose our boundary condition and demand that the field be regular everywhere. And the regular solution obeying the boundary conditions I want to impose is just so the part with Bessel I is not regular, and this is the part that's the regular solution, and it explicitly obeys my boundary condition. At z equals epsilon, I get phi naught. Okay, so we have all the pieces in place. We've solved explicitly the wave equation, and now by the rules of the game, I'm supposed to evaluate the action of the field on the solution, which will give me a function of phi naught. I vary that to get my 2-point function. Okay, so the 2-point function well, now I'll write the 2-point function not in coordinate space but in momentum space. And I'll write my source phi naught also in a Fourier expansion with Fourier coefficients lambda 1 and lambda 2. Okay, where W is S phi evaluated on the solution. Now clearly there's nothing very fancy in terms of evaluation. I got rid of the action. But it's clear that if I take this action for anything that satisfies the field equations, if I integrate by parts, the only thing I need to evaluate is a boundary term. Right? If I integrate once by parts, I'll get an equation of motion which I integrate over, which is 0, and then there's a boundary piece which I have to take care of. So all the contribution here comes purely from a boundary term that I need to worry about. So this part is not so hard. So you evaluate the boundary term, and what do you find? I'll write everything in terms of this quantity, because it will be clear what that quantity means in the field theory in a moment. There are some gamma functions coming. We're looking at the Bessel function. Okay. So I have made a couple of simplifications here in writing this, and for my purposes, I'll tell you what terms I've dropped, but for my purposes, it's going to be good enough to restrict attention to this bit of the boundary term. What I've dropped here are some analytic terms which go like epsilon p squared. So this is just p, not p vector. And I've also dropped some terms which are non-analytic. I've just kept the leading non-analytic bit in P. If I kept any of the other terms, when I eventually Fourier, what I'm going to do is Fourier transform this back to position space, I will get contact interactions which I'm not keeping track of from the point of view of the conformal field theory. Now, this is a sort of quick and easy way to do the regularization. You can do things more properly in the framework of holographic renormalization by taking care very precisely of all the contact terms and so on, and introducing the appropriate counter terms. That's something I'm not going to talk about. So you Fourier transform this back. And lo and behold, we have an expression for a 2-point function. I'll explain this hash in a moment. So there's some large set of prefactors that I'm writing down which are completely irrelevant for my purposes, but just to show you that we can get a sensible result. The thing that I care about is this bit, a bit that goes like x minus y to the power minus 2 delta. Okay. So what is this hash doing here? Well, the thing is, I didn't tell you what was the proper normalization of my scalar field action in the bulk. I picked some arbitrary normalization, and if I wanted a properly normalized 2-point function, I would have to figure out what the precise normalization was between the operators on the boundary and fields, the coefficient in front of the quadratic part of the action for the fields in the bulk. Okay. So that's the hash. There's a bit that goes like epsilon to the 2 delta minus 8, and there's some overall coefficients here which I can again absorb into my undetermined normalization. But the operative part is the fact that this has the right properties of the conformal 2-point functions of operators of dimension delta.
To some power will be cancelled by this hash, yeah?
No, so the epsilon some power we'll have to deal with. This is a cutoff. This is a regularization dependent thing. The hash is some numerical constant, which I am not worried about. So then the conformal dimension of the operator here is exactly delta, and by the relation here, I have derived for you a relation between the scaling dimension of operators in the conformal field theory and the mass of the corresponding field in the bulk. Okay, so an operator of dimension delta is dual to a bulk field whose mass is given by this formula. The relation is precisely given by that formula. Okay. So this is the answer, and to sort of wrap up, I have to answer the question that was just asked, which is, what is this bit proportional to epsilon to the 2 delta minus 8 doing here? Well, what I'm going to do in the scheme of things that I'm talking about is to absorb this factor into my definition of the operator. So my regularized operator will have some powers of epsilon, and this, if you like, is my prescription for working with the cutoff theory. So at the end of the day, my 2-point function is just
Say nothing about this number.
for the moment. So for particular fields, by looking at sort of how the field theory operators couple to the bulk modes in the parent D3 branch theory before decoupling, you could say something about this number. Okay, but for most fields, I can't. What I'm going to do when I'm going to discuss the 3-point function is sort of get rid of this ambiguity by choosing a basis of operators which are canonically normalized. So I'll explain that in a moment. But in general, the answer is no, I can't say anything about this number for arbitrary operators.
So you don't have an overall normalization then?
I don't have an overall normalization that works. If you like, it's a sort of issue of there's a space of operators for which I'm calculating 2-point functions, and I haven't told you what's a good orthonormal basis in that space of operators. Okay, so this calculation that I did was reasonably straightforward, but I did it in momentum space because it allowed me to do things very simply. You didn't have to do it. You could actually, the original calculation which was done by Witten was done directly in position space. And let me just quickly indicate that to you, because that makes better contact with the formulation I gave yesterday of propagating fields on the boundary into the bulk. Okay, so yesterday I wrote for your formula where I said I can think of this problem as solving some standard boundary value problem and writing down a kernel which takes my source and gives me what the bulk field is. So the calculation that I just did can be repeated directly in position space to figure out what this kernel is. So this bulk to boundary propagator for scalar fields something very simple. Okay. There are many ways to think about this, and there's a very easy way to actually motivate why this is the right bulk to boundary propagator based on sort of the underlying symmetry of AdS space, which I won't get into. But what you can go back and check for yourself is that this guy reduces to the right delta function at z equals 0. So it reduces to delta x minus x prime, which is what you would need in order for phi at z equals 0x to be phi naught. And this presentation also makes it very clear of how I should sort of visualize this calculation. To make contact, let me draw this picture of AdS, the Euclidean AdS, as a disk. The boundary was at z equals 0, but I implemented a regulator at z equals epsilon to do this computation here. And the prescription is very simple. You should think of k x prime as follows. Pick two bulk points labeled by xz and x prime z prime. Calculate the Green's function in position space for propagation of a scalar field in the bulk, and then take one of the bulk points out to the boundary, in this case out to z equals epsilon. So there is some power of, so let me write it this way, with some regulator which I have not prescribed here. So this is clearly the bulk to bulk propagator is clearly the bulk Green's function. It's just a Green's function for a scalar field propagating in anti-de Sitter space. Okay, it's just a standard 2-point function calculated in Kerr space. I'm taking one of the legs of that Green's function out to the boundary, but if I want a boundary 2-point function, I should take the other leg also out to the boundary. Okay, let me call this k bulk to distinguish the two k's. Boundary 2-point function is just the bulk to boundary propagator with one leg taken to, with the bulk leg taken out to the boundary and some powers of z stripped off. This power of z that I'm stripping off is exactly this epsilon to the 2 delta minus 4 that I stripped off in this regulator. I should. So that I didn't write that, so I should have written this as. Thanks. So I would need that for sort of regularity of this object, so I get a non-zero answer. Okay. Okay. Now there are some subtleties if I want to compute correlation functions in Lorentzian space, and what I mean by these fall-offs and these issues which are already asked before. What I'm going to do is first continue with this computation and sketch for you what happens for 3-point functions before getting back into the subtleties of what happens in the case of Lorentzian calculations. But before I do that, any questions about the 2-point function that we just computed? So now, rather than sort of go through the exercise of doing the whole thing again in momentum space, let me use this simple form of the bulk to boundary propagator that I derived and quickly sketch how to compute the 3-point function. So I want to compute the 3-point functions of 3 operators inserted at x1, x2, and x3 in the boundary, and their conformal dimensions are delta 1, delta 2, and delta 3 respectively. So what do I do? Let's do this pictorially for the moment, and then write down the formulas that would be relevant for us to compute. So I could again sort of try to look at the bulk fields dual to my operators, and let's call them phi 1, phi 2, and phi 3. And the bulk Lagrangian has kinetic terms and mass terms for the scalars. But importantly, the scalars have to couple at least by a 3-point function in order for this 3-point correlator to be non-zero. If the scalars don't couple in the bulk, then those three operators will have zero correlation function in the boundary. And the masses are related to the scaling dimension via the equation that I just erased. So delta I okay. So I determine the appropriate fields in the bulk by making sure that they give me the right conformal dimension for the operators on the boundary. So what do I do here? I take my bulk fields, I give them sources at the insertion points on the boundary, and from there on propagate them inward into the bulk using my bulk to boundary propagator. And when I come over to evaluate the action, I have to evaluate this term. Okay? The field phi, to compute a 3-point function, I use the free propagation. I'm going to do this in perturbation theory in lambda. So I use the free propagation of phi to solve for this part of the action. And the 3-point function needs variational derivative with respect to 3 sources. So I need a term with 3 sources, which is and one which is linear in each of the source, and that comes from this term in the bulk. So I have my 3 fields, and in the bulk, at some point x z, the 3 points are brought together by this interaction term. So diagrammatically, what I want to compute is precisely this kind of diagram, but the point where the 3 sources, the 3 fields meet can be anywhere in the bulk, because there is an integral over the bulk point. So I have to integrate over this point throughout the bulk. So to finish off this diagram, here was x1, x2, x3. And the term of interest is nothing but the term proportional to lambda and now I will replace phi's by the solution to the free wave equation in terms of the propagator that I just had before. Okay. So this is just in equations what I said in words. You use that free propagation and plug in to the cubic term in the action, and you're left with an integral which is this. Okay. And then there are source bits. I'll get rid of this because this is the final answer. I'm not going to write the intermediate step. There's a minus sign if I want to be precise about my signs. Okay. So you have an expression for k. You have the integral. That's the homework.
This lambda in the action is what?
Okay, so that's the point we'll come to. So let me write down the answer for the 3-point function, and then we'll come back to lambda. And you find, if you do the integral, that you get an answer that's the following. Clearly, the integral is just a function of x1, x2, x3. And by conformal invariance, we know the position dependence, but it's reassuring to check that the very same position dependence on the insertion points works out precisely from doing this bulk integral. Where I've used A to denote a function of delta 1, delta 2, and delta 3, and some constants which come from doing the integral. What I've written here is just the dependence on x1, x2, and x3 obtained by doing that integral up there. I will write down what A is and then answer the question about what this coefficient lambda is, because there is some very interesting physics hidden in lambda. This coefficient A happens to be some ratio of gamma functions I'm just writing this down, but the only way you're going to be able to appreciate where these come from is by doing the integral, which I'm not doing for you. I'll give you a reference in a moment. Okay, so this is what this integral works out to be, and here you have an explicit 3-point function for 3 primary operators in the conformal field theory whose dimensions are delta 1, delta 2, and delta 3 respectively. Okay, so now I'm in a position to answer two questions that were raised. One was, what on earth is the right normalization of the 2-point function, and what is this lambda? Okay. So what I told you before is the following. I have some fields propagating in bulk AdS space, and I sort of don't know what the proper normalization for all operators is at the level of the 2-point function.
Is the last parameter in the numerator?
It's in the numerator. It's up. Yeah. So I told you that sort of the coefficient out front is not something I know explicitly for all operators. However, if I sort of choose my supergravity normalization in some canonical fashion, I should be able, by expanding my supergravity Lagrangian out to cubic order, be able to fix the relative normalization between the cubic and the quadratic parts. That is fixed to me by the bulk action. In fact, all these terms here, the cubic pieces, come from expanding out the Einstein action in supergravity. Okay? So while I can't give you an absolute normalization for the 2-point function, I can give you a precise ratio of the 3-point function divided by properly normalized 2-point functions. Or rather, if you define a basis of operators in the field theory which are orthonormal, yeah, I've just used I1 and I2 as some overall indices. I'll make it precise in a moment what operators I'm considering. Then I should be able to unambiguously ask what is my 3-point function. Let me stick to my notation. Where the dependence on the coordinates is exactly what I have here. Okay, I haven't written the numerator yet, but let me just write down at least one term. Okay.
Actually, may I ask
Yeah, please.
a couple of questions?
Yeah.
First of all, is this action involved bounded from 0? I mean,
Yes,
okay.
it's positive, definitely.
And the second question is, can you have kind of loops in this Witten diagram? I mean, these results you get for coordinate functions are fixed by conformal symmetry at the boundary.
Yes.
So they are precise. But what happens if you consider the higher order terms in the action, and it will change the coefficient? Yeah.
Okay. So let me postpone the second question for a moment. I'll come back to it once I finish explaining this bit for the 3-point function. Okay. So there's a special class of operators that I was mentioning yesterday, these chiral primary operators, and I'll describe you to them in field theory terminology, which is where this index I came from. So the notation I'm going to use is as follows. I'll describe for you the chiral primary operators in the conformal field theory as symmetric traceless k-rank tensors built up from the scalar fields in n equals 4. Okay, so the Cijk, this tensor here is just an SO6 tensor which is rank k, symmetric and traceless, making sure that this whole object transforms appropriately in the field theory. So I take the chiral primary operators in the field theory and make sure that I normalize them such that I get this 2-point function. Okay. Then I go away in the field theory and compute in the 't Hooft expansion at large n, but at small lambda I compute this 3-point function. I get an answer which is this. Where this gadget here is a particular contraction of symmetric traceless SO6 object, some group theory object which you can explicitly write down, but I'm not writing it down for you. The other point to note is this 1 over n, which is guaranteed by large n scaling. In large n expansion, we said higher order, we can play the same game that I gave you the first day for computing vacuum to vacuum amplitudes in computing correlation functions of operators. And you should see that if you compute properly normalized correlation functions of operators, 2-point functions are order 1, 3-point functions are of order 1 over n, and higher point functions are order 1 over n to the appropriate power. An n-point function should scale like n to the 2 minus n. This is computed at weak coupling.
Yeah, but there is no coupling.
There is no coupling here. This is computed at tree level. This is the tree level answer. I don't think there's a 't Hooft coupling in there. You go away and do this computation by realizing the fact that for these chiral primary operators, I can identify what phi's I want to work with in the bulk. Okay, so you identify the phi's. Of course, part of the identification is simplified because they have to have the right conformal dimension and they have to have the right tensor structure. So it's purely kinematical at this level, identifying the phi's associated with these chiral primary operators. In fact, it's completely dictated by symmetries, so it's not so hard. And for that class of fields in the supergravity, you go away and figure out what this coefficient lambda is. Okay, you can do it. It's a bit of a exercise, but it's a straightforward expansion of supergravity action to cubic order. You get an answer. You take your 2-point functions computed in supergravity, normalize them to be this, and then ask what your 3-point function is. It's exactly this. Okay? The answer you get at strong coupling calculated in supergravity is exactly the same as the answer you get done at small lambda in perturbation theory. This is an example of a non-renormalization theorem in this case for correlation functions of local operators, but very similar in spirit to the kinds of things Brian was talking about earlier to you in the context of n equals 1 theories. Here is a much higher supersymmetric theory, it's n equals 4, the maximal supersymmetry in 4 dimensions, and there for a class of operators, these chiral primary operators, which in some sense are like BPS objects in the theory, they're the sort of, in operator language, what you would want to call BPS states, their interactions governed by this 3-point function remains unchanged. Okay. So before I answer the question, if anybody is very curious to figure out how to do that integral, the answer is in a paper by Friedman, Mathur, Rastelli, and Matusis from early 98. Okay. So now let me wrap up the discussion of correlation functions by answering the question, how do you compute endpoint functions? So in order to compute endpoint functions, what would I need to do? Let me illustrate this for 4-point functions, and I'll ignore symmetry channels for the moment. So I'll have 4 operator insertions on the boundary, and I would have a supergravity Lagrangian, which schematically would have terms like, we'd have kinetic terms, mass terms to give me the appropriate conformal dimension, cubic couplings, now quartic couplings, we want to call them, and I'd have to keep the action out to this order to be able to compute 4-point functions. Okay, there's one contribution that we would get from the source terms, which is easy to see, which is contribution analogous to our 3-point function coming from the 4-point vertex in the bulk. I propagate my bulk boundary fields into the bulk, and then intertwine them somewhere and integrate over the bulk insertion. That's a simple thing. But there's also 3-point vertex in this theory, so I can bring together these guys pairwise. And then connect the bulk insertions by a bulk to bulk propagator. Just propagate my field from here to here by a bulk to bulk propagator. So those will be contributions coming from these type of terms in my supergravity action. But then it's clear what you want to do. If you want to compute loops, you could go ahead and compute loops here. If you want some arbitrary endpoint function, you certainly can compute diagrams like this in supergravity. This should give you higher corrections to endpoint functions in supergravity, but still in the large n limit.
Corrections with respect
to the in the bulk it will be alpha prime corrections or lambda corrections, but not they're still in supergravity, so it's not string loops, it's supergravity loops. Okay, so these computations can be done. Some 4-point functions computations have been done already in literature, but I'm not going to describe them to you in detail. So I'll refer you to the literature if you're interested in knowing how to compute certain of these 4-point functions. Okay, and now in the remaining bit of time, I want to talk about one aspect of the correspondence, which is something I've alluded to in doing the correlation function calculations, but I haven't talked about in detail, which is the distinction between Lorentzian and Euclidean AdS CFT. There's an important distinction to keep in mind, and there are some subtleties which were confusing in the early days of AdS CFT as to how to do the Lorentzian AdS CFT, which I'll describe in a moment. But any questions so far about the correlation function calculations? Good. Okay. So in Euclidean AdS, let me just for the moment stick to the discussion in terms of scalar fields. You could generalize it to other fields propagating in AdS, but it won't change our discussion so much. If I consider the quadratic part of the action, then the only non-trivial solutions which obey the boundary conditions are those which are not normalizable at infinity. Okay. Now, what happens is if I sort of solve the scalar wave equation, then it behaves as follows. I'm just rewriting in slightly different notation, not very much, something that I had written before. Where phi naught, as usual, is my source term. Okay? So my field behaves at small z exactly as follows. And it's this fall off with z which makes this not normalizable. Provided, so delta, remember, was obtained in terms of the mass of the field, and now for complete generality, let me just give you the answer for delta in AdS d plus 1. So clearly, when d it's AdS 5, you get 2 plus 4 times square root of 4 times m squared r squared, which I had before. So it's this bit which is not normalizable, and once you have a sort of any field which sort of falls off at some rate at leading power, there's subleading bits to it, and there's a lead, and this subleading bit given by A is a response of the field to the fact that I turn on a source. Okay? So what should you think of this? I have some operator in the boundary. I can couple my operator to a source and insert it into my Lagrangian, as I was doing yesterday in sort of motivating how I would write down generating functions for correlation functions. So my new Lagrangian is undeformed Lagrangian plus in the CFT, this is the CFT, and phi naught is the source, and that's the part that couples the operator. So phi naught, the source, corresponds to the non-normalizable mode of the bulk field. Okay? And how should you think about this? In adding a source to my Lagrangian in the conformal field theory, I'm changing the rules of the game. I'm changing the Lagrangian of the field theory. So in the bulk, I should do something similar. I have to deform the asymptotics of my space-time. In particular, I have to add something that's not dying off too quickly. That's what will change the dynamics. The system will respond once I deform it, and what I have in the bulk is this response A. This is a wave or an expectation value for O in the field theory which it picks up in response to the source. Okay? And there's a very simple relation between the source and the wave. In fact, the wave of the operator O in the presence of phi naught is nothing but A up to some normalization, but which I've introduced to make some things nicer later. Okay.
It's all done for Carroll primarily.
Actually, no. This is true for any operator in the field theory. Anytime you can use supergravity. I'm still talking about supergravity. Okay.
What is the value of delta for n-dimensional tensor?
So so delta is 4, but I'm talking here about scalar fields. So in order to talk about the energy momentum tensor, I would have to look at an object in the bulk which has the same tensor structure and symmetry properties as the energy momentum tensor, which would correspond to a mode of the graviton in the bulk. So yesterday you saw, for example, when you want to look at currents, symmetric currents in the field theory, you're looking at vector fields in the bulk. Okay, so this is the story in Euclidean field theory and Euclidean AdS, and things are all nice provided okay. The requirement that I have real conformal dimensions for my fields translates into a bound for the masses of fields in the bulk. The masses have to be bounded from below by minus d squared over 4, and this is called the Brighton-Lono-Friedman bound. In the context of field theories in anti-de Sitter spacetime. Now, if you are doing the same analysis in Lorentzian space, there are non-trivial solutions to the field equations where I can switch off the source and have just normalizable modes. They, in this language, correspond to just turning on waves for operators. So in Euclidean field theory, I can't do that because in AdS there are no non-trivial solutions. But in the Lorentzian theory, I could very easily turn on just a wave for an operator and define a state in the field theory. So a simple example is turning on a wave for the energy momentum tensor, putting finite energy density in the conformal field theory, giving the stress tensor expectation value, which in the bulk corresponds to putting a black hole, which has, if you look at it, it's an asymptotically AdS spacetime. It doesn't have this phi naught bit turned on when I look at the graviton, but it has this A bit turned on. Okay? So this is the distinction we have to keep in mind when you're going between Lorentzian and Euclidean AdS CFT. In the Lorentzian context, we certainly can have perfectly nice normalizable solutions, whereas the only non-trivial solutions in the Euclidean context are ones where the field is not normalizable at infinity. Okay, so that sort of wraps up the basic story of AdS CFT in the context and sort of what you would compute in terms of correlation functions in this framework. Tomorrow I will sort of talk a little bit more about black holes in the AdS CFT correspondence. Okay.
Any questions before we break the coffee? Okay, let's thank Mukund again and get some caffeine.